Okay, so as I said at the end of the talk, I'm just going to give my full talk here because, first of all, I think it's useful as a reference, and second of all, we didn't have time to go through the whole thing. This talk is not, I don't get into any technical details. The purpose is only to give a general conceptual understanding of what's going on. If you want to see the mathematical details of how we arrived at the arrival time distributions using our own preferred model and using other models to compare them, I think Sidon's papers are really a good reference for that. So I'm going to begin by, well, first of all, let me say, I'm going to do this talk as if nobody had seen the original talk. So I'm giving the whole thing again. Now, I'm going to start by, well, I think the most clear way to introduce the arrival time issue is to describe a concrete example of an arrival time experiment. It's going to be schematic, but I think it's going to give a nice impression of what the arrival time issue is. So we begin over here. The wave function is prepared at an initial state, and the time at which that initial state is prepared is known. Now, for our purposes, a particle is going to be inside a Paul trap. And in the Paul trap, there's going to be some kind of wall which prevents it from escaping a small region of the trap. At a time which is chosen by the experimentalist, that door is opened. That means that the particle is free to move inside the trap. And the time at which the door is opened is recorded. I'm calling that t equals 0. After t equals 0, the particle travels via the Schrödinger equation. The particle hits a detector. Now here I've pictured a screen. It may be a wall of laser light, which triggers a photomultiplier. We still have to figure out the details of which detector is best. But regardless of which detector is used, it's necessary that the detector is coupled to some kind of timekeeping device. That timekeeping device records the time at which the particle arrived. Of course, there may be a delay in the arrival time because it's necessary for the signal to take time to stop the clock. That can be accounted for, but after that is accounted for, the arrival time of the particle, which is the quantity which is measured by the experiment, is the difference between the time at which this clock was triggered and the time at which the door was opened so that the particle can move freely. So let me say that again. On each run of the experiment, we start with an initial state, we let it move freely, and then we record the difference in times between when the door was opened and when the particle was detected at the screen. Now, we expect that even when one starts with exactly the same initial state, and even in an idealized setup where there are no errors, the arrival time is random. It's the same sort of quantum randomness that you can imagine in other variables. loosely speaking. Of course, there are different sources behind it, but I don't think that's relevant to conceptualize the experiment. So that means that what's being measured is not a particular arrival time, but the distribution of different arrival times. Every time this experiment is repeated with the same initial state, the experimentalist records the time at which the particle arrived. Now, when the experiment is done many times, the histogram of the different arrival times of the particle makes a distribution. This is the measured arrival time distribution. And in theory, it's called capital pi of t. Now, capital pi of t is something new to many physicists. So I'd like to talk a little about what it means. Capital pi of t is a probability density function. That means that when you integrate this function from time a to time b, it gives you the probability that the particle arrived between time a and time b. Equivalently, you can say that the probability that a particle arrives between time a and time b is the area under the curve pi of t between ta and tb. Of course, in order for pi of t to have a probability interpretation, you have to normalize the histogram first, so that the area sums to 1. Okay, so what exactly is pi of t? As I mentioned, when explaining this problem to other physicists, one common reaction is, well, isn't pi of t just somehow the Schrödinger evolution of the particle? Can't you solve for the time-evolved wave function through the Schrödinger equation? Now, we can solve for the time-evolved wave function, but I want to emphasize that that is very different from pi of t. I mean, for one, it's clear because they're not even functions of the same variable. Psi depends on position. For the setup, which we hope to work with you guys on, Sidont has already calculated the exact solution to the Schrödinger equation, giving us psi of x and t. Despite that, there's no agreed upon theory on how to calculate pi of t, despite the fact that it's an experimentally testable quantity. For a little bit of further intuition on pi of t, let me give an analogy to some other variables in quantum mechanics. If a measurement is done at a fixed time, then the probability of that measurement giving a position x, the probability density, is the inner product of x with the wave function squared. The probability distribution from momentum can be given in the same way. You take the inner product of a momentum eigenstate with the wave function and square that. That's equivalent to taking the Fourier transform and squaring it. Interestingly enough, when it comes to arrival times, there's no prescription in quantum mechanics which gives you the distribution of arrival times. the traditional way to derive a probability in quantum mechanics is by starting with an operator corresponding to the observable being measured, finding the eigenvalues and eigenvectors of that operator, and then forming a probability density with an inner product of those eigenvectors with the wave function, or with the state. For time of arrival, there is no known time operator. Not only do we not know of a time operator, but I'm aware of two different proofs that a time operator isn't expected to exist as long as it has physical properties that one needs from either the time operator itself or the eigenstates which it would produce. This hasn't stopped some physicists from making time operators, which then necessarily don't give those physical properties that are expected. But this is the origin of the arrival time problem. And it's the reason, the lack of a time operator is the fundamental reason why arrival times is an open question in quantum mechanics. Now let me give just some background on why I'm excited about this problem. So first of all, the concept of the problem is very simple. You start with a particle in initial state. It reaches the detector, you record the time, and you just repeat that experiment many times. As I said, I've managed to explain it to my mom, and even she can understand, though she's not a physicist, what this is all about. I don't know of any other case in which a problem can be so easily stated, and yet the theory doesn't even have a solution to the problem in principle. I'd like to distinguish a problem which has no solution in principle from the more common theoretical problem in which one knows the equation which should solve the system, but it's just a matter of solving that equation, but the algorithm for coming to the solution is known, it's just too difficult to solve. That's a common situation in theory. This is a rare situation in theory in which, even in principle, there's no framework within quantum mechanics to calculate the arrival time distribution. And for that reason, it's possible that the results of this experiment will fundamentally move the theory. And I am being generous when I say that it's possible, because actually, no matter what the experiment shows, it's not going to be any standard distribution, because there is no standard distribution in this case. It's really, there's a great potential for this to have an impact on theory as a whole. And that's why I'm excited about it. Now, I'm going to discuss the arrival time problem in theory. Like I said, I'm not going to go into any technical details. I'm just going to give a general feeling of where the theory is at currently. And I would say the theory is quite messy right now. And that's exactly why an experiment would be extremely useful in this problem. So let me draw your attention to a review paper by Muga and Livens, who both have published quite a bit on the arrival time problem. In this review paper, they go over quite a few of the different approaches to predicting arrival times. And I've outlined some of those approaches in red, just so that you can see there's really a lot of disagreement in the theory about what the correct answer to this problem could be. I want to say that even this paper, which is a really nice review of all the different experiments, sorry, the different models that exist, it doesn't capture even all of the models that have been proposed and are written about in the literature. So, which one is the correct proposal? We don't know. We can't possibly know, and that's really why we need help from you guys. It would be an amazing help to the theoretical community to be able to eliminate some of these proposals in a clear-cut way, because currently theory is going in circles, just arguing with itself about sometimes even just aesthetic reasons why certain distributions are better than others. And arrival times really needs the scientific method. Now, in our view, of course, you're speaking to the group of Bohmians. So, of course, in our view, the Bohmian proposal is the most reasonable. But let me substantiate that a little bit by giving some background on myself. I've always been interested in the foundations of quantum mechanics. But 1 year ago, I had a very different perspective. I went to some student conferences in which Siddhant gave an introduction to Bohmian mechanics. And it was actually my goal at the time to prove Bohmian mechanics wrong in some way or another. I mean, the field of different interpretations of quantum mechanics was just too large, and I was hoping that it would be possible to rule this out because many physicists are very pessimistic about Bohmian mechanics. So I took it upon myself to try to find a concrete experiment which could rule out Bohmian mechanics. And in doing so, I actually managed to convince myself that Bohmian mechanics is a really valuable theory. And not only that, but that I don't expect it to ever be ruled out. And I think, well, at least in the non-relativistic regime, it's still necessary to expand it relativistically. Anyway, I think one manifestation of the clarity of Bohmian mechanics is the fact that it's even able to make a prediction for the arrival time distribution pi, whereas ordinary quantum mechanics can't. So it's not quite right to say that the two theories are equivalent. Now, I'd like to make one thing clear though. This experiment is not about Bohmian mechanics. We happen to come at it from a Bohmian perspective. But there are physicists who come at this problem and would be very interested to see the result who aren't in support of Bohmian mechanics. Maybe they believe in one of these other models by Muga, or written by Muga. And we're not looking to prove Bohmian mechanics right. We're just looking to find out what is the right answer to this problem. And regardless of what the result is, it would be very interesting. I'm going to point out now that in order to derive capital pi of t, it's necessary, or at least very helpful, to have an exact solution of the Schrödinger equation for the potentials which are realistic for the setup which you guys can make. And I continue to be really impressed by things that Sedant has done in solving the time-dependent Schrödinger equation for potentials which are increasingly more and more realistic. It's really noteworthy work, and for those potentials, the Schrödinger equation had never been solved before. And it's because of this work that it's now possible to compare theory and experiment. It may have been possible without, but it's not very clear, and certainly it would have been difficult. So this is a big step in the theory. Here I've just included a figure which compares different distributions for the setup which we hope to work with you guys on. This pi SC, where SC stands for semi-classical, this is something like the distribution that I think Henri presented on, and it involves quantum mechanical initial condition, but classical trajectories. We have many more proposals which will actually be compared in experiment, so this graph is just a subset of those. For a spin 1/2 experiment, this would be the expected shape depends on the initial condition of the particle for Bohmian mechanics, in particular the spin initial condition. A particle which starts with spin up has a different arrival time distribution in Bohmian mechanics than a particle which starts in a superposition of up and down. That's not true for the semi-classical distribution. So even seeing a dependence on the initial condition would be very interesting. However, this is for a setup with spin 1/2, and it seems reasonable that one can first eliminate some of the important distributions through a simpler experiment with a spin 0 particle. But I'd like to point out that really the spin 1/2 experiment would be, in the long term, incredible to know the results of. I'm almost done on the theory section, but I'm just going to give a really brief review of what is the Bohmian approach in particular. It's quite likely that you've heard about Bohmian mechanics before, and if there's anything you've heard about Bohmian mechanics, it's that you know that the particle moves on well-defined trajectories. Let me make that a little bit more detailed for you. These trajectories are not classical trajectories. In fact, it's necessary to know the wave function at all times in order to predict the trajectories. The trajectories move according to the guidance law, which is here. With spin, there would be an additional term, but I haven't included it for simplicity. The guidance law works by defining a velocity field at all points in space. Then the particle moves through flow lines of that field. But the velocity field, since it depends on the wave function, changes in time as the wave function changes in time. This defines a unique trajectory for a particle given an initial condition. One might ask, how can it be that Bohmian mechanics is deterministic, whereas standard quantum mechanics is random? The randomness exists in Bohmian mechanics as well, but it's not an intrinsic randomness in the same way that it is in quantum mechanics. The randomness in Bohmian mechanics comes from the fact that the initial position of the particle is not known. The initial position of the particle is distributed with a probability proportional to the wave function squared. Now, I'd like to point out that often it's viewed as a postulate that the distribution of initial positions of a Bohmian particle is psi of r and 0. However, there are very good arguments from the guidance law itself to suspect that pausing the evolution at a random time, you would find that only due to the motion given by the guidance law, the particles will be distributed as psi of x at a given time. So it's not strictly necessary as a postulate, but this is something which both Siddhant and Professor Dua can speak more about. Now, it's well known that if a position measurement is done of the particle, the result for the probability density in quantum mechanics is the same as the result for the probability to find that particle in Bohmian mechanics. And that probability density is given by psi of r and t squared. So in all experiments up to the present day on non-relativistic quantum mechanics, Bohmian mechanics gives the correct result. The question is whether Bohmian mechanics will now also give the correct result for the arrival time distribution of a non-relativistic particle. There are attempts to generalize Bohmian mechanics to the relativistic case, and some of them have been successful, but to generalize Bohmian mechanics to a Fock space presents difficulties. I can't claim that I am an expert in that, and I'm not going to speak a lot about it, but it seems that there's hope in the relativistic case as well, but work has to be done. Now, just for your imagination, you can see a typical trajectory here of a Bohmian particle. This is from the setup which we would actually like to do in collaboration with your group. Motivations for the arrival time issue. I'm just going to speak briefly about why I consider arrival times important to begin with. I already mentioned in the first slide that it's very rare in the year 2020 to find any case in which quantum mechanics is unable to predict the result of an experiment in principle. And it's, as far as I know, unprecedented that the concept behind such an experiment is so simple. Now, if you think about what is necessary to make a fundamental discovery in physics, for many years now, it's been believed that everything is known in quantum mechanics, and the only room for improvement is quantum field theory and quantum gravity. That has had a remarkable impact on the focus of the physics community. And it's believed by many physicists that at this point, in order to make new contributions to the theory, the only experiments which are known, which can be done, are collider experiments. Collider experiments have therefore defined the progress of theoretical physics in the last 50 years, at least theoretical particle physics. It's gotten to the point where there are so few experiments known to the community that governments are willing to spend billions of dollars for a single experiment to see if new physics can be found. For that reason, taking this perspective, it's absolutely incredible that there is a theory here which is not possible, there's an experiment here which is not possible to be derived in theory, and progress can be made outside of experiments which cost on the order of the entire National Science Foundation's budget for a whole year. So I really strongly believe that this is an incredible opportunity, and I'm very excited to see the results. This problem has been known about for a long time, and it's a difficult question to ask or to answer why it hasn't been addressed in the mainstream yet. But I say, let it be that way. I think for everyone involved, this is really an incredible opportunity to potentially be part of something which could be important to the development of theory. Now, on that note, I just wrote a quote here by Misra and Sudarshan, which they wrote almost 50 years ago, pleading both theory and experiment to spend more time on problems like arrival time. Maybe because experiment wasn't ready at the time to make these kind of measurements, not very much progress has been made since then. We're now beginning to see a resurgence of this, and it's very encouraging. And that's the end of my talk. This is the point at which I would have asked for questions, but we had a nice dialogue with everyone, and questions were really fluently asked during the talk, which I think is great. But I just really want to say that maybe I've been kind of formal in giving this talk, but I'm really chill, and I am happy to talk anytime to anybody. And I'm really excited about this problem, and I am happy to spend as much time as necessary on it. So if anybody has any questions, like, just message me over email, send me a message on WhatsApp. Make sure you include the +1. I'm from the US, and my number is still from there. I speak English. Ich spreche auch Deutsch. Also, wie du willst. And really, I think communication is important in a collaboration like this. So yeah, I mean, feel free to even just say hello. How are you doing? But really, I'm happy to answer any questions that anybody has. So hopefully this is useful to you guys. And yeah, bleibt gesund.